In the last part of this video series, we looked at how the PMU works and how to configure the channel registers. You just point to the descriptor list, initialize the loop variables, and set the channel to run. Now we're ready to look at the descriptors themselves. The instruction sets for most CPU cores typically consist of dozens of instructions, and that goes for even so-called reduced instruction set cores. But the PMU is a purpose-built logic block, and it specializes in moving data around, so it only needs 8 instructions. That is, 8 descriptor types. Each descriptor is 32 bits wide, and additionally, each descriptor takes from 1 to 4 32-bit operands. Today, I'm going to show you each of the descriptors and describe all the bit fields that make them up. But here's the good thing. You don't need to think much about the physical layout of the descriptor elements. Maxim provides libraries that let you declare the descriptors as though they were simple C functions. Let's start with a move descriptor. The move descriptor does pretty much what the name implies. It moves data from one point to another. All you do is tell it how many bytes to transfer, where they come from, and where they go. And the PMU does the rest, but there's more to it than that. There are a couple of bits in here that are common to every descriptor, the int and stop bits. Int stands for interrupt, and if the int bit is set in any descriptor, the PMU sets the int bit in that channel's status register. And if the interrupt enable bit is set, the PMU channel will wake the main CPU core. The stop bit stops the opcode processor after it finishes running the current descriptor and sets the bit in the status register that tells the main CPU that the PMU channel stopped normally. Both the int and the stop bits are available in every descriptor type, so any descriptor can alert the core or halt the channel as needed. There are also a set of fields that set the read size and the write size, 8, 16, or 32 bits. Now, here's the cool thing. The PMU automatically packs and unpacks bytes, words, and long words when the data source isn't the same size as the destination. So if you're reading from, let's say, a UART that delivers received characters as 8-bit bytes, the PMU can pack 4 bytes into a 32-bit long word before it writes the data to memory, and in the process saves bus cycles, time, and power. There are also bits that control incrementing the write address and the read address. Now here's why. If you're transferring data from a peripheral, let's say a UART, to memory, you want to read the UART received data register over and over from the same address. But you want to increment the write address in memory. In this case, you'd clear the read increment bit and set the write increment bit. Now there's one more bit in the move descriptor to talk about. If the continue bit is set, the opcode processor ignores the read and write addresses and continues moving from wherever the last transfer ended. Now, to me, here's the interesting thing. If all the PMU had was the functionality of the move descriptor, well, we'd have to say it's a pretty capable DMA unit. It moves data, it performs word and long word pack and unpack, it works on any address, and there are 6 channels that can do all this stuff at the same time. The thing is, we still have 7 descriptors to go. Let's take a look at the write descriptor. Now, in its simplest form, the write descriptor can write a fixed value given in the write value field to any address given in the write address field. But the write descriptor can do much more than just writing values to memory. Each time it executes, the write descriptor really performs a read-modify-write operation on any location within the ARM memory map. And for some operations, it only modifies the bits that are set in a third field, the write mask field. If you load the write mask with all ones, then the contents of the write value field will completely replace whatever's stored at the address given in the write address field. But you can mask the write operation so that only certain bits are modified. This makes the write descriptor perfect for clearing only certain fields in peripheral registers. But there's more. The write method field works like a mini opcode to tell the write descriptor what to do. You can increment or decrement the value at the write address, shift, rotate, or invert the value, or perform OR, AND, or XOR logical operations. In a sense, you have kind of a baby ALU built right into the right descriptor. Our third descriptor type is wait, and it does just what the name implies. The wait descriptor causes the opcode processor channel to wait for some event to occur before proceeding. The 64 bits in the two operand words are augmented by a select bit to provide up to 128 possible events to check. And if the wait bit is set in the wait descriptor, the channel lets the given number of clock cycles expire after the selected event occurs before proceeding to the next descriptor in the list. But what kind of events can we wait for? Well, pretty much anything. You can wait on the status of any FIFO, any communications peripheral, and the ADC, including limit checks. And you can wait on an RTC match. You can wait on a pulse train, on a timer, on the crypto subsystem. I mean, after all, some cryptographic operations require a significant amount of time to complete. You see, there's a lot that you can do without waking the CPU at all. Our fourth descriptor is also the simplest, jump. Like a jump instruction in a CPU instruction set, it just tells the opcode processor to begin fetching descriptors from somewhere else in memory. No other operands, no modes, just jump. The fifth descriptor is loop. Loop works like a decrement and jump if not zero instruction. It decrements the selected loop counter 0 if the cell bit is 0, and loop counter 1 if the cell bit is 1. And it jumps to the given address if the result is not 0. Now, notice that the contents of the loop register never actually change. When you start the PMU channel, the value from the loop register is copied to an internal counter. So if you stop and restart the PMU channel, the loop counter gets restored to its original value. It's also reloaded if the internal counter ever gets to 0. So you never have to explicitly reload the loop counter in your PMU program. The poll descriptor is a little like the wait descriptor in that it waits for a condition to become true. But while the wait descriptor monitors interrupt lines and status bits, signals that don't require access to the system bus, the poll descriptor actually generates bus cycles polling memory locations or peripheral registers to determine when some status changes. Here's how it works. The opcode processor reads the data at the address given in the poll address field and compares only the bit positions set in the data mask field to those in the data expected field to determine if the match condition is met. But here's where it gets a little tricky. See, in some cases, the data you're polling might be a collection of condition flags, and you want to continue to the next descriptor if any of those conditions become true. But see, in other cases, you might be waiting for a particular value to appear in a register, in which case you're interested in matching the value of all the bits under the mask before you continue. Well, that's what the AND bit in the poll descriptor is for. If the AND bit is set, the match condition is satisfied only if all the selected bit positions in the data expected field match the data read from the bus. You'll set the AND bit if you're polling for a particular value appearing in a peripheral register or a memory location. But if the AND bit is clear, the polling condition is considered met if any of the bits under the mask in the data expected field match the data read from the bus. You'll use this option if the register you're reading contains a set of condition flags and you want to proceed if any of those condition flags becomes true. Now, if there is no match, then the descriptor waits for the number of PMU clocks given in the polling interval field, and the process begins again. Now, why do we want to wait? Because unlike the wait descriptor, the poll descriptor is actually generating bus cycles. If the flag we're watching changes only infrequently, and our application can tolerate the latency, it's better to poll the location infrequently. That keeps the PMU from using too much bus bandwidth, and it reduces power consumption. The seventh descriptor type is branch. Now, you may have wondered about conditional jumps when we covered the jump descriptor. Well, wonder no more. The branch descriptor is the conditional jump, and the condition is taken directly from the poll descriptor. The poll address field, the data expected field, and the data mask field work exactly the same as they did in the poll descriptor. There is one field unique to the branch descriptor, the BR type field. This field defines the conditions under which the branch will be taken. If the BR type field contains 0 or 1, the conditions are evaluated just as they are in the poll descriptor. The bits that are set in the data mask field directly identify the bit positions to be compared in the addressed memory location and the data expected field. And the match condition is met contingent on the state of the AND bit. If the AND bit is set, then all identified bit positions must match, and if the AND bit is clear, then the condition is met if any bit position matches. BR type 0 is branch on not equal. That is, if the match condition is not met, the branch is taken. BR type 1 is branch on equal. That is, if the match condition is met, the branch is taken. BR type values from 2 to 5 are arithmetic comparisons, so the values given in the data mask field and the AND bit don't apply here. The entire data expected field is treated as an unsigned integer. A BR type value of 2 performs a branch if the value read from memory is less than or equal to the expected value. A value of 3 performs a branch if the value read from memory is greater than or equal to the expected value. A value of 4 performs a branch if the value read from memory is strictly less than the expected value, and a value of 5 performs a branch if the value read from memory is strictly greater than the expected value. In all cases, the comparison is unsigned. Now finally, there's one last descriptor, the transfer descriptor. This works a lot like the move descriptor, but it has an additional feature. It moves the data from one point to another in blocks, perfectly sized for getting one FIFO's worth of data in and out of memory. Now here's how it works. Just like the move descriptor, you load the transfer length, the write address, and the read address, but you give it a couple more pieces of information. The interrupt mask, where you tell the opcode processor what FIFO bit to monitor, and the burst size, which should match the depth of the FIFO you're using. Now when the opcode processor runs a transfer descriptor, it will wait until the bit you've specified becomes set. The FIFO full bit, if you're moving data received from a peripheral to memory, or the FIFO empty bit, if you're moving data to be transmitted from memory to a peripheral. Once the FIFO condition is met, the opcode processor channel performs a block transfer for the number of bytes you specified in the burst size field. When just that data burst has been transferred, if it hasn't transferred all the bytes you declared in the transfer length, it'll wait for the status bit again before transferring the next burst. Now in this way, the data gets moved in blocks until all the data is moved. Well, that's it. Just 8 descriptor types to learn, and now you know them all. In the next video, we'll move from the classroom to the lab, and we'll start looking at the PMU demo project. It's in your distribution media, and it's a simple program, but it'll show you exactly how the PMU can automate some tasks while the main CPU sleeps. You're not going to want to miss this. I'll see you then.